Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, welcome back. So, we have seen how a feedback control implementation is done and what is the transfer function when we look at the closed loop of a system by using a feedback control. In this lecture, we will now look at what are the basic control actions which are present when we, or which are possible when we try to implement a feedback control system or feedback control strategy. So, those are mainly proportional action, integral action and derivative action. So, we will look at what is the rationale behind each of those actions. We will then analyze the closed loop response of a system when the system is subjected to these controllers, and lastly we will see what is the effect of controller parameters and what sort of dynamics does it have when we change some of the parameters of the control system. So, before moving forward, let me just clarify the actions of a feedback controller. There are two distinct types of actions which a feedback controller has, and depending on the type of action, the controller parameters have to be chosen. If we choose that wrongly, then the controller will not be able to do the job for which it is installed. So, we first need to look at whether the controller is going to be direct acting or reverse acting. So, in order to motivate these, let me consider two implementations of feedback control. So, the first one is the same as what we had looked just a while back. So, it is the feedback control of level. So, we are trying to control this level, this is the disturbance, and the way we do it is we first measure the level. Accordingly, it is compared with the set value. That error goes to the controller, and then that controller will take an action and make a change to the valve, and then finally you will get the change into the manipulated variable, which is f out. Now, let us consider a second example. Again, the system we had considered earlier is the stirred heater or stirred tank heater, where you have some feed coming in at temperature Ti and you want to control the temperature inside this vessel to some value T, and that is done by changing the heat flow into this system. So, in this case, if we want to implement feedback control, what we will be doing is we will first measure the temperature. So, that is temperature indicator, then that will be compared with the desired value of set point, and then it will go to the controller, which is the temperature controller, and the output of that controller will change this manipulated variable, which may be the steam flow rate, which will change the duty or the heat duty supplied to this particular system. So, both of these are feedback control systems, and I would like you to pause for a bit and try to see if there is any distinction or any difference between these two feedback controllers. Okay, so welcome back. I hope you were able to find the distinction between these two systems, and if you have not, then let me go over it. So, in both the cases, let us look at what happens when at the steady state you will have your output is equal to the set value. So, in both the cases output will be equal to the set value. Let us say at some finite time, because of some disturbance, this y increases beyond the set point in both the cases. So, in this case, as y increases, which means the height inside this tank increases, what is the control action that is needed to maintain the level? That your output should also increase. So, which is same as the controller output should also increase. So, if I represent u as the controller output, then it has to increase when my height increases, which ultimately results in increase in F out. Now, look at this case of the stirred tank heater. Let us say the y increases beyond the set point, that means the temperature inside this tank is above the desired value. Now, what should the controller do? It should actually cut down on the heating duty supplied to the system. That means the controller output should decrease. So, now you can notice the difference between these two systems. Here an increase in the output causes increase in the controller output, therefore, it is known as direct acting controller. In this case, increase in the output causes a decrease in the controller output, therefore, it is known as reverse acting controller. So, it is very essential that you know what is the type of action of the feedback controller, whether it is direct acting or reverse acting. If you use a reverse acting controller to control this particular process, you will realize that the level will never be maintained by any type of feedback controller. Similarly, if for this particular system I use a direct acting controller, again the system, this feedback system will never be able to maintain the temperature to its desired value. So, the first and foremost thing before even deciding what type of a feedback control we want, what type of feedback control action we need in terms of the proportional, integral or derivative action, the first thing you should be trying to find out is whether your system is going to be a direct acting or a reverse acting. And this is not that straightforward when we look at the industrial implementations of systems, because a same system may give you direct or reverse action depending on the type of actuator which is inside the process. So, this will try to explain this. Let us say we have the same example of liquid surge tank. And here we considered that as the valve opening increases, or I would say valve signal increases, F out increases because the valve opening increases. So, these types of valves are known as fail close valves, which means if there is no signal given to the valve, the opening will be 0 and the flow out of that valve will also be 0. So, if that is the case and if we implement a feedback control onto this system, which will be of this form, then this feedback control system will be direct acting. But for this same system, if we have the valve which is known as a fail open valve. So, the same system which is generally represented in its piping and instrumentation diagram by a small subscript FO. So, the implementation is exactly the same. But what you now see is, as this is a fail open type of valve, as valve signal increases, the wall opening decreases, or that means F out decreases. That is because when the wall does not have any signal, the valve is completely open, or the wall has 100% opening. So, if that is the case and you try to find out what happens when the height increases, in that case you will realize that in order to increase F out, the controller signal will have to reduce, and because of that, if it is a fail open wall, then the same feedback control system would be reverse acting. You can see that same system, only difference is the actuator type. In one case the actuator is fail close, and this other case the actuator is fail open. Just this small difference is going to make the controller to be either direct acting or reverse acting. And as I had said earlier that if we use or if mistakenly use this to be a direct acting controller, it will never be able to maintain the level. And as we look at the control systems, we will see why that is the case on a more mathematical at a higher through mathematical analysis as well. So, it is very important to know what is the type of the controller action. So, let us now look at what are the different type of control actions which are possible in feedback control. And the first or the simplest control action, simplest in terms of implementation, is on off control. So, on off control is one of the very commonly used control strategy, feedback control strategy, which is for very low key objectives or very cheap control systems will have on off control action, and those refer to, let us say, if you have a thermocouple or temperature controller in your house, then those typically are on off type of controller. In your lab, whenever you had some sort of a flow or a temperature controller using a small heater, those are also typically on off type of controllers. So, on off controller, the philosophy is that the controller output depends on sign of the error. So, all you are interested in is what is the sign of the error, whether the error is positive or error is negative. You do not even look at what is the magnitude of error, and that is why it is very simple or easy to implement, and depending on the sides, depending on the sign of the error, control action is taken. So, let us say if the controller is direct acting, and if y set minus y, which is the error, if it is greater than 0, then u will be equal to the minimum value of u. If y set minus y is less than 0, if the error is negative, then u will be made equal to the maximum value of u. And the exactly opposite pairing works when we have reverse acting controller. So, you can see that all we are interested in is just checking whether what is the value of y in relation to y set. If y is less than the set point and if the controller is direct acting, then the manipulated input is kept at its minimum value, the moment y becomes greater than the set point value, the manipulated input completely shifts the direction, or it goes from the minimum value to the maximum value. So, the only two values which the manipulated variable can take is the u max and u min, and in typical physical systems, this u or refers to the opening of a valve, some sort of a controller valve, and then that means the valve will go between completely closed to completely open position. So, typically this would be completely closed if it is a fail closed type of valve, and this would typically mean completely open. So, the valve will continuously move between the maximum open and close. So, it will be toggling between the two values continuously, and as there is always some lag associated with the measurement and the controller to take an action, the valve to open or close, the system will never be able to reach the value of y set. So, continuously y will go above and below the set point value, and the valve will keep on toggling between the closed and open positions. In order to, because of that, the valve will undergo severe wear and tear, and then the valve will have to be replaced, or it will have mechanical failure quite often. In order to avoid that, there is a concept of a dead band which is added to this on off controller. So, instead of taking action as soon as y goes below or above the set point, there is some dead band is provided between which no control action is taken. So, the same on off control in the presence of dead band will look like this. So, if the controller is direct acting, y set minus y, rather than greater than 0, we look at greater than some positive number, then u becomes u min. If y set minus y is less than the negative of that number, u goes to u max, and then if this y set minus y is between these two values including 0, no action is taken. So, if the valve was earlier at minimum position, it will remain at minimum. If it was at maximum position, it will remain at maximum. So, because of that, during this interval, or there is generally some freedom given for this y to remain below the set point without taking any control action, and this significantly reduces the toggling or the on off moving of the valve from on to off position quite often, and because of that the valve life gets extended, and this dB is known as the dead band. It is the band between which no controller action is taken. So, the larger the dead band, what is going to happen is that the valve will have less toggling, but at the same time you are allowing the output to go that much. So, you are allowing the output to deviate that much from the set point. So, the effect of dead band is, so as the dead band increases, y set minus y increases. So, that means the I will say average value of that. So, that means larger deviation from the set value, but this comes at an advantage that our valve toggling reduces. So, this dead band the higher dead band is used to avoid the valve to go from on off position at a much higher frequency. So, typically the dead band is selected based on the trade off between how much deviation is allowable and correspondingly how much wall toggling is allowed. So, as a trade off between these two, the deadband gets selected. You can see that this on off controller is very easy to implement, but it has a significant disadvantage. The two of the main disadvantages. The first of all, it cannot maintain the set value. So, if we want to control the variable exactly at the set point value, then on off controller will not be a good choice. And secondly, so as the wall toggles a lot, the life of the wall is reduced. So, it will only be used for very non-critical control objectives, where a significantly large deadband will be used to avoid the wall toggling, and you are still okay by having that much of an offset. So, one of the examples from real life is level control in intercooler for air compressor. So, what happens is whenever you are trying to compress air from ambient conditions to some higher value, you would typically go with multi stage compressors, and as the compression of air is going to increase its temperature, in order to maintain the efficiency of compression, you have to cool that air stream before it enters the next level or next compressor stage. As we are dealing with air, air also has a capacity to hold moisture, and as you compress the air and reduce the temperature after this cooler, there is a possibility of condensation. Condensation of water at that point. And if we have this two phase mixture of air and water which goes into the compressor, again that is very detrimental to the compressor blades. So, at that point there is a requirement that you collect this liquid and then remove this liquid after the heat exchanger. Now, as it turns out, this level builds very slowly, and typically there is no objective in terms of controlling this level apart from the fact that you do not want this particular vessel to get completely filled. So, the level control on this particular after cooler is typically on off type of controller, which controls a solenoid valve which is at the outlet of this. So, when this level goes beyond a certain value, this valve will open and empty out this entire contents. Again it will get closed when the level goes below the desired value, and then the system will again operate till the level gets filled up. So, these kind of very low key non-critical objectives will be the places where on-off controller will be used on an industrial scale. So, thank you.